for, okay. For this class participation, it will show up, don't worry about it, it's very slow. And not that your methods are wrong, but here's the thing, you learn some of this from your other classes, then you can take my classes and I teach you the way I'm teaching it, and then you come and solve it from your other classes method, right? It makes it difficult for me to understand what you did because I might not be familiar with their method. The whole idea of me solving problems in class and giving you new ways of solving things is that you follow them, all right? Now, if your final solution is correct, then it's correct. But in your homework or your exams, I'll grade based on what I taught you, okay? And usually there is a reason for the topics that I teach you. They are related and building on top of each other for the next module, next topic, right? For example, to write H01, there are different ways doing it, but the way I taught you is this is a homogeneous 4x4 matrix. We know this is going to be R01, P translation or the origin from 0 to 1, like 1 and 0, 0 and 1, right? All you have to do is to find the rotation matrix between the two frames and the translation between the origin of the two, as seen in frame 0. So what you should do is say, okay, R01, you could use the projection method, or if you want to do the dot product with cosine, it is also fine. But right now it's super easy to say, okay, this is X1. So X1 has 0 component in X0 direction, 0 component Y0 direction, and -1 in Y0 direction. Then if this is your Y1, so I'm bringing the axis down to just show you how I'm doing it. So 0, sorry, this is 1, then 0 and 0, and then for Z1 is going to be 0, -1, 0. So that is your R01. P01, or the translation or the origins, are the origin of this 101 in this frame, 0. So you see that I'm going to delete these so you can see what's happening, right? So this is lifted or moved from from the origin of the frame 0 on the y-axis direction for 1, and then there's no translation in z and in x and y. So there will be 0, 0, 1. So your H01 would be 0, 1, 0, 0, 0, -1, -1, 0, 0, and then 0 for all of those, 0, 0, 1, and then we append with 1. So this is faster. I've seen you had other methods. If you do them correctly, not that they're long, not that they're wrong, they're longer. If I give you this in exam, this took me what, 2 minutes? I'm giving you 5 minutes for this. Now, if the exam is 55 minutes, I designed this for 5 minutes. It's your choice to spend 20 minutes doing 3 4x4 matrix to find this one. Then you will not have enough time for the rest of the questions, right? So it's good to follow this method. It's quick, it's accurate. You can always check back where you went wrong. But if you do 3 matrix multiplication, because some of you did the rotation about, okay, this first matrix rotated, first reference rotated 90 degree about one axis, then 90 degree about the other axis, created 4x4 matrix. You multiply, you get a wrong answer. Now to check, you have to go back through every single one of them. Also check your calculation, right? So you're checking error also takes time. So I would prefer if you use this method. It's a lot easier. Sounds good? All right. So that I will post this solution on Carmen under my solutions. And then, sorry, didn't mean to do that today. Okay. So today is going to be a little bit math heavy. So you want to be like, this is one of those days you want to be here 100% of the time. So hopefully you will not zone out for more than 30 seconds. Okay. We'll start with simple reviews from differential equations. If anything there, yeah, I said review, and you're like, this is the first time I see it. I need to know, because to my knowledge, these should be reviews. And we will use them a lot. Okay, so Let me know if these are not reviews and they're like first time you see these things. So you can consider a simple scalar linear differential equation. X dot of t is a x of t. A is a scalar, right? And our initial condition at time 0 is x0. So we have initial condition. You have seen this before, right? It's the equation of a line. Correct? You can tell it, right? Now, if you get this equation, the solution to this would be x of t is e to the power of a of t times x0. You can calculate that, but you should know this is the solution. You can remember it. You plot, if you solve it in MATLAB plot, it will give you the plot for this equation. You'll see that it's always like this. So if your a was a scalar, it was a number, your solution is e to the power of that a, whatever it is, times t in time domain, right? So solving a differential equation, times x of 0, which is your first initial condition at time 0. Now, if we have a vector, for vector linear differential equation, it kind of follows the same pattern, but this time x dot of t is ax of t. Here A is a matrix. All right. Now, the solution would be x of t e to the power of a of t, which A is a matrix. Now, this x, this is a vector. What does it mean we say x is a vector? So if you were to write x of t, it would be x1 of t, x2 of t, all the way to xn, depending on how many, what's the order of that. So did we talk about the state here before? It could be position, velocity, pressure, time, temperature. So those are those, and x is the vector of all of those states, for example. We also know, have a name for this expression, a to the power of e to the power of a of t. We call it matrix exponential. We are going to use matrix exponential next week when we are solving our forward kinematics. All right. So A is a matrix that is in Rn by n, meaning that is either 2 by 2, 3 by 3, 4 by 4, 5 by 5, right? So and this makes e to the power of a of t to be also Rn by n in that space. All right. So what do you need to remember from here? That the format of the solution of this differential equation. So if I make a differential equation, we don't need to solve it. We already have just to remember. And that this is a matrix. These are things that you need to remember from this. Now, a couple of properties of this matrix exponentials. The derivative of our matrix exponential, which is a to the power of at. So when I said matrix exponential is the whole a to the power of at. The derivative of that always is going to be a times e to the power of at. You can also, since this is a matrix, you can bring, and this is a number, you can bring this behind it or after. So if you need it at some point, move them, flip-flop them, you can. You're allowed to do that. Because as a number times a matrix, so it doesn't matter which way where it is. Now, if your A matrix is in the form of P times D times P inverse, yes. When you calculate, it becomes a number. When you have numbers in your matrix, it becomes a number. Thank you. So if A is that expression, we can define A, that expression, if for some D matrix in Rn by n. So for, we don't know what D is. We are just assuming any matrix that's 3 by 3, 4 by 4, 5 by 5. if you can define an invertible matrix of P, which then P inverse exists, is definable, then we can write e to the power of AT is this expression. So basically you're doing this. E to the power of P D P inverse times T would be equal to P E D T P inverse. We can write that expression. If A and B are a matrix, and if both of them are matrix, and AB is equal to BA, if we can show this relationship, then e to the power of A times e to the power of B is going to be e to the power of A plus B. Do that then. So these are all matrices, right? And the inverse of e to the power of A is to the power of negative. So we're going to use these properties later on when we are proving something, or sometimes we use them. Do you need to memorize them? No. Do you need to know where they are? Yes. So this lecture, or put it on a cheat sheet somewhere that's accessible, right? I try to have a system to rename my lectures, but usually there are so many content in one lecture, I can't just put all the names on the title of the lecture. So try to find a way that works for you so you know where the information are. All right. This is a topic, if you remember from first week, that I said we will talk about that later. Now that's the time. How many of you have heard about skew symmetric representation? None. One. Okay. Two. Okay. Great. So three. All right. So good. It's new for almost everyone. So when you say symmetric, what does it mean? If a matrix is symmetric? Yeah, like if you think about the diagonal elements, everything above and below are the same, right? The triangle above and below, they are the same. Skew symmetric, they are lopsided. So there is a negative. So they are the opposite sign. They're the same number, but they're opposite sign. That's why we call them skew symmetric. Now, why they define this? We use this later on in converting or simplifying our cross product, because we're going to use cross products a lot when we are solving our forward and inverse kinematic. And skew symmetric is an easy way because it converts cross product to dot product. So we can just use it. All right, so that's why we're learning this. There are two properties that the skew symmetric matrices have. S transpose is equal to negative S. That's basically why they're called skew symmetric. Which means if you add S transpose and S, the result is going to be 0, right? And the determinant of S is 0. So when we say and, it means that, like, let's say I'm asking which one of these are skew symmetric. So you're going to do this. Let's say for this one, you check first if S transpose is equal to negative S. If it wasn't, you don't need to check the second one, because based on logic, one of the conditions did not pass, right? You have to check the other one. If it was the same, you want to also check if the determinant is zero, right? You always start from this though, that if the transpose is negative, it's easy to visually see it. But you can't say every one that you see visually skew symmetric is going to be skew symmetric. Now, tell me which one of these are skew symmetric. Spend a minute or two, follow those, and then for A, B, C, D, find for each one. Basically, find their what could be the skew symmetric version of them. So here, I solved this one. Transpose is 1, -2, 2, 1. And then if I add them, 1, 2, -2, 1, plus 1, -2, 2, 1. This is going to be 2, 0, 0, 2. So this is not. So for 2 by 3, you need to check that. For 3 by 3, you can check just S transpose is equal to S negative S or not, and then. Like this showed up in the exam where I'm actually right now. And tell me this.
Yeah.
You really need to show me report, otherwise they don't. I don't think you work for it. Sorry. All right, so for this symmetric, so hopefully you have. You look at the 3 by 3 that diagonal elements are 0 and the off diagonal are not 0, but they are opposite in sign, right? Which is here. So this is the form of a skew symmetric. So now, how do we use this? So we know how they look like, right? We just checked, and then you're able to see if one is or one is not. Now, we use them to convert our cross product to a sum. And calculations are a lot easier that way. Your book's notation, I think, is slightly different from this. I think there's a squiggly mark on top of it. If you see that, so whenever you read literature again, pay attention. What are the notation? Everyone use different notation. I think though this is your book notation. I think I checked. I fixed my slides to match. So A cross B is defined as skew symmetric of A times B. Right? We also show skew symmetric as S of A. So A and B are vectors, right? So if it are in N, so A times B, so it's N by 1, so 3 by 1 no matter 2. So you'll be able to actually do the cross product. It has to match dimension. Then you can define SA or skew symmetric, or you might see it in bracket A equal to this, where your A is defined as A1, A2, A3 means that you have 3 components, and this is how you distribute the components to form your symmetric. So this is some new definition, something you fabricate. There is a proof that this actually works, but you're not going to bother yourself with that. But this implies off diagonals are 0, on diagonal 0, off diagonal, they just have a negative sign. So there's a sign difference, they're the opposite. So for any given A vector, you can write the skew symmetric of that vector. It's a 3 by 3 matrix. All right. Because that's the definition, A cross C, the first vector becomes a skew symmetric, not the second. The order is important. It's a definition. You follow the definition. There's no why, not the other way around. Now, here's an example. If A and B are as such, and bracket A is defined as a skew symmetric, I want you to show me what the skew symmetric of A is, and then calculate A cross C using the skew symmetric method, not cross product. This is where you should be able to do matrix multiplication by hand. So that they're not too difficult, but you should be able to do them. I know you don't like it, but life is not fair. Like I didn't like Coco cooking the house last night. All right, and does anybody have the final? Yes. -4, -4, 5. Anybody has my solution? Yes. Oh, listen to student. It's probably when you are calculating, so first row times the column, and then you need 100%. I've done it many times. So you are the 4th generation in this course, so most of the titles are gone. Should be pretty good. I still have some, but most of it. Well, because think about it. When I started, like now I basically know all of that, but in my head, my first language is not English, and I know all of them in a different language. There's a quick translation that happens here to you, and it comes back, and I solve math in my original language. I don't do English. I do all of it in Farsi, and then I translate it into English when I count. So it takes a while, and sometimes when I'm doing it and writing, what I say and what I write doesn't match. That's why most of my titles are from there. I'm getting better though, like I'm trying to count in English and all that. Yeah, I've been here for more than 10 years too. Does this make sense? Like how the math works, right? But all you have to remember is A cross C is that bracket A times B. All right. Sweet. Fun stuff starts now. This is where we use those differential equations. So this, until here, I wanted to make sure everybody remembers that such things exist. You remember in your differential classes, like you're never going to use it. If you work in robotics, you'll use that. So your life was not wasted, basically. So we will talk about linear velocity and angular velocity because that's the 2 types of velocity we will encounter in a 3D space, right? One comes from position translation along XYZ. The other one is because we are rotating about an axis, so we have angular velocity. Now, for a moving particle with a coordinate of P of T, so we are in time domain. That's all it means. When we are in time domain in 3D space, we can write the linear velocity as V of T, which is P dot of T, the rate of change of the position. And we can write D, or the derivative of PT to dt. So these are the notation. We can use them interchangeably at any time. They all mean the same. What does this physically mean? It means that if this is your Z, X, and Y axes, and you have a point P that is moving on a path, a robot moving on a path, right? If this is the tangent at that point on the path, you have a direction and a value, right? So that would become your velocity. So velocity has a value and a direction, so that velocity is a vector. We're gonna hold both of those. So this will be P dot of T. Now, if we have a prismatic joint, you're working on your homework now, so you'll see prismatic joint, right? Your prismatic joints can move or slide, right? What would be the direction of the velocity for that? Depending on which way it's going. So if we said that our prismatic joint is going this way, so this becomes your velocity. Now, wherever that is, it could also, we call it P dot of T. If you call the center, if you put a point, a reference frame on the center of that joint, and then you're moving it, then that's the direction of the velocity as well, right? For prismatic joint, what kind of velocities we could have? Only linear, right? It's just a slide along your axis, your principal axis. Now, whenever we have rotational motion, then it becomes more interesting because we have angular velocity. Now, angular velocity happens because of the rate of change in the angle of rotation. So let's say you had theta angle at the beginning, at time t plus delta t, you move delta theta. This rate of change will give us the angular velocity. So theta dot becomes d of those delta t, well, those delta t over, so let's say, yeah, over small t, but then we're going to write dt. So you're incrementing over time. As they get smaller, then we can write the differential of that. But now this is just the amount of angular velocity, right? We also need to represent the direction. To represent direction, we can add or multiply by unit vector. So since it's a unit vector, it doesn't impact the value of the velocity, it doesn't go up or down. It just tells us which direction is happening. So since we are in 3D direction, we expect our vector to have 3 components, right? What's the velocity in 3 different directions? So that's why whenever we talk about angular velocity, we use this expression. We say omega is omega hat theta dot. Omega hat is that vector, that direction, tells you which way this velocity is happening. All right. Now let's say that you're rotating about this axis, some omega, right, with theta. Now, whenever we have angular velocity, we also generate a linear velocity as well, right? So if you have a rotary joint, you could have 2 kinds of velocities. When you have prismatic, you only have one type. We're going to use these for forward kinematic. So that's why we're starting from here. So the linear velocity that is generated because of this angular velocity, here, if you think about your particle is moving around about this axis, about the around this circle, it would be the tangent of that. So x dot is omega cross product of s. That's how we show it. Because when we do cross product, this generates the direction and the magnitude, right? That was one way to show the direction and magnitude for that. If we wanted to write what is the velocity in y direction, we say omega cross product y, z dot omega cross product z. Now, sometimes you might have just x dot, sometimes might have z dot, sometimes might be a combination, right? But we always write those equations, some of them will be zero, depending on the direction of your velocity, which comes from the direction of the rotation. Now, I want you to look at the that figure on the right side and pay attention to the origin of that axis on that frame. So the rotation happened around an arbitrary axis, right? The rotation could happen about z-axis. Right now, your omega has x, y, z coordinate. You remember the general case that we saw is a big matrix? This is that general case. The simpler version is when it happens, the rotation is about only z or only x or only y. So the general case is the one that could have all of these, but if it was just about z, then you could only have, you have reduced number of velocities generated there. Now you see that that axis is passing through your origin. This is really important to understand and to identify if the axis of rotation is passing through the origin of the reference frame that you're measuring your velocity. If that's the case, then you can write the rotation of velocity as x dot of x, the vector, right, equal to omega cross product of x. That becomes your velocity. Now there is a case when it doesn't pass and the equation is different. So you want to make sure every time you see a rotation is happening and you are asked to find the velocity, then you want to see if the axis of rotation passes through the frame or not, the frame that you're moving. Okay. If it does, is the simplest case, that is a simple equation for you. As a cross product, you can easily convert it to a dot product. How? It's skew-symmetric, right? Omega is a vector. We just talked about it. It's 3 by 1. You're gonna write it 3 by 3 multiplied by x of t, which is also 3 has 3m as a vector, right? So you can put that. So if you were here in 3D mode, 3D space. So you see that becomes a lot easier to solve than if it was just cross product. So assuming that you're still in the case that the rotation happened, the axis of rotation passes through your frame. What does it mean? So think about this as part of an industrial robot, right? This top part has an R joint, solid. So this whole thing moves together. So it rotates from here, and you want to know what's the velocity of this side here. But you want to know with respect to your reference frame here, S. These are all the same rigid volume. You can define our reference frame anyway, right? So if we define the body frame here, okay, this and this now are having their origin are aligned, right? So we're making our problem easy because now that this is the easy case. If this rotates, the axis of rotation passes through the reference frame. So V becomes omega cross product of X. Now, how do we define, how do we also count this little distance here? So if I have a point P, let's say here, and this will start rotating, does this distance change? Let's say it's P, it's always going to be P, right? Basically, you're saying there's a point that is, let's say this is VXY. Distance P on the y-axis of our reference of our body framing, right? It's rotating about the z-axis, and this z-axis passes through this. Does that make sense? What is happening here? So let's say this is your point P. This is the rotation. You're rotating this way. So this is VS, which is your P dot, right? I'm gonna not use S yet. So that's P dot. Here is your theta. This is the variable, right? This is your, let's say your R joint. I can say this is a constant P constant value. So if I call this B frame, I put the frame of this rigid body on that center, this becomes PB. The position of point P, which is at the center of the arm in body frame, is going to have some value in this space all the time. Because the body frame is moving with it. They're always in the y-axis, right? Doesn't change with respect to this stuff. But it changes with respect to this one, because this doesn't really do that, right? So we want to find what is the velocity of this P point P in S frame. So we are trying to find V of S, which is P dot of S, rate of change of P point with respect to S frame. We identified a body frame, which is this, and the origin line. So rotation, if this was your R, what's the axis of rotation here? ZB, right? And then let's say this is ZS, XS, YS. So you see that the axis of rotation is passing through our reference frame. So we are in the simple case of X is just the cross product. X dot is the cross product. So we can write V of S is P dot of S. And then we can also say PS is RSB PB. Why are we doing that? I'm just going to show you that there will be a rotation between these two frames. If we have the rotation matrix, right? If we have this rotation, we know this point P in this frame, we also know it in this frame. Agreed from before? Going that way. All right. So we have two ways of doing this. We could say that P dot of S, if this is P, is going to be D RSB PB DT. Now, to get the differentiation of this expression, we can simply get the differentiation of RSB. So D RSB DT and bring PB outside. Why can we do that? is a constant value with respect to the body frame, right? So we can say that this expression is, we can call it R dot of SB. So every time you get to this expression, you can say, because this is element wise, so you have 3 by 3, you can get the differential of every element. So you can say D R T T R dot. So if you see here, VS became R dot SBPD. So if you have the position in one frame, you want the velocity of that in the other frame, all you have to do is grab the rotation that you already found, get the differentiation of that effective time. So if you think, if you're programming this, you only need to find your rotation matrix once. Then you have all the position and all the velocities in your new frame. Make sense? Now, what if the rotation doesn't happen in the axis that goes through your reference frame? The example would be if your point, so if this was your rigid body and your point was here, you're trying to find the velocity of this point, the rotation axis is here. So you will define your body frame, let's say like that. And then the body frame and your S frame, they are offset by Q, some value. All right. Then your P dot becomes omega cross product of the distance of the two origins measured at all times. Right? So this time your P is changing, but then you have to keep taking that Q off of it to find the new position. So all we do, we put that PT minus Q, so updating the new origin of the two at all times. That's the only difference that you'll see here. Now let's use the skew symmetric version. So this is omega, and then we multiply by PT minus Q. Thank God, now we can just expand this, right? Because now we are in the realm of dot product, and we can simply write that. Does that make sense? Just simply opening up that equation. And we could do that because we use a skew symmetric. Now this bracket omega is a 3 by 3 matrix. It's not 3 by 1 anymore. It's already in a skew symmetric. How do we put it in a skew symmetric? You already have the matrix that you can do that, right? So to write the velocity in matrix form for all cases, we are going to combine these two together, these two cases. So we wanted to write here. You don't know for a general case if the rotation is going to happen along the reference frame or there's going to be an offset, right? Remember from PA1, we write the code for general case. We have to solve this equation for general case too. We do a little bit of math magic here. Just follow me. So this was P dot of T. So I can write this in matrix form. So this is the right side compared to that right side. P dot T is 0 doesn't matter, right? Now, if you do this, you get to that expression. So all we did, you put this in matrix form. Now, this is your P dot, This is your A matrix, this is your P, which was your X, right? So X dot AX, vector matrix. Do you know the solution of that? Yes, e to the power of 18 times x0, right? So we change this, so basically use math to put it in a form that we are familiar with and we know what the solution is. So once we have this, all we have to say, hey, MATLAB, use OD45 and solve this for me. If you never heard of that, what I said, there will be PA for that, PA assignment for OD 45. How to solve differential equation using MATLAB. That's your next one. All right. So what if your rigid body just translated about an axis, like the case that we already saw, the first degree of velocity, and we put it in a form that kind of resembles this, and then we can just use them as a universal equation. So let's see if we can do that. P dot of t would be v prime, some velocity, right? So let's say this has P dot P of t is this, P dot is some velocity on a linear function. Now, I'm going to use the magic again and say P dot of t and 0. So you see that those two sides are similar now, is equal to 0, 0, v prime 0 times pt 1. Because I want this to look like that and this guy to look like that. Then I can combine them. Now, why did I write like this? I need a 2 by 2 matrix because that's what I have here, right? Now, 0 times p is 0 plus v prime times 1 is v prime and 0, 0. So I just put this in matrix form. Now I have both of them in the same format. Now I have the universal equation for the velocity for all types of motion in previously. Now it doesn't matter what it is, I do value values. All right. The things that you need to know where they located is this guy and this guy, plus how to calculate the skew symmetric. Make sense? So like put a note, leave a note for yourself. How tired are you? Not? Raise your hand if you're tired. Okay, it's okay. All right, because the next two slides are a little bit heavier on math, and I see your face already melting, and then you did a good job of keeping me excited. So in reward, you get 5 minutes of your life back. So you cannot do the quiz yet. I'll leave it for Monday, but then you could do it in the class. It's super simple. It's basically in the lecture, but I need to go over it. All right. So I see you on Monday. Nothing for the weekend. Work on your homework. I'll see you on Monday.